In this video, I wanted to talk about a couple of different decisions you have to make prior to doing the analyses. And then this video I expect to be fairly short. And the next video most likely will be actually walking through some R code to show you how to do these invariance tests in R. And a couple of the issues we talked about last time, just to kind of rewind those real quickly, is really related to kind of pragmatics. What are you going to test for, which item parameters, those kind of issues, and then sample size, which is a more pragmatic issue. But there's some more complicated issues as well. And one of those relates back to the topic we covered just before this section on linking. So if you remember in the last section on linking, we kind of talked about what do you do if you're introducing new test items to a data bank, right, or an item bank. And in that case, what we kind of talked about is that when you're estimating both item parameters and theta estimates simultaneously, you have to make some kind of constraint on the data to identify the model. And that's an IRT thing, but it's also something you see when looking at confirmatory factor analysis. Same issue comes up. There, typically in that literature, you typically pick one item and you kind of set that value, the loading for that item to 1.0, or you set the factor variance to 1.0. And it's essentially the same kind of thing in item response theory. So you can either set the variance of the latent trait to 1.0 and the mean to 0, which is kind of what most of the software does, or you can make one or more items, sort of what we call a bit like anchor items, I guess is what what you might talk about them. And we saw that again last time in the linking video. In that case, what we had was a situation where we had, for example, some people get some common items, some anchor items that are the same across the two groups, and then the groups get different items for the other items, and we learned how to use that, what we learned through the anchor items, in order to put the groups in the same metric. And the reason we had to do that is because if you just estimate both item parameters and thetas separately in each group, typically the software will default to setting the mean theta to 0 and the standard deviation of theta to 1. Now, if you're comparing groups, that's a problem because that makes an assumption that the groups are absolutely equal in the latent trait. And a lot of times that's actually kind of what you're testing, right? You actually may have a hypothesis that the groups differ on this variable, and you're doing invariance analyses just to make sure the measure performs the same way. So that's not really the approach we want with multi-group analyses, typically speaking. So we have to find another way to sort of set the metric in a way that we know that scores across the two groups can be compared. So we want to set the metric in a way where we're not setting each group kind of within group mean of theta to 0 and a standard deviation of 1. So we're going to use anchor items to do that. So basically what anchor items involves is we're picking some subset of items and saying these items behave the same way in the two groups. We know that. And again, this is not unique to IRT. The confirmatory factor analysis literature does the same thing. There, usually you pick one item, you say this item is known to be functioning the same way, and you make this assumption that it's functioning the same way in the two groups. So we're going to do something a little bit like that. And I used to have a whole lecture on comparing CFA approaches to measurement variance to the diff approach in IRT, and I may have time for that later on. But it's a little bit different in IRT. The two literatures developed entirely independently. And in IRT, we usually use a multi-stage process in order to do this linking between groups. So one way to do it again would be if we had an item that we knew functioned the same way in both groups, we could set the metric based on that one item alone. We could set the item parameters for that one item to be equal across the two groups, and then we can estimate freely the thetas and all the other item parameters, and that would allow us to compute and compare the item parameters to make sure they're the same in the two groups, and also compare thetas if we have invariance. So we have to figure out how to choose these anchor items, and there's a couple different ways to do it. There's actually several ways to do it. The most common approach historically in the IRT literature is to use something called the all others as anchors approach, AOAA, all others as anchors. And typically, this is where you're doing invariance test where we are using a constrained baseline model. So if you go down to the bottom here, this bottom bullet point on this slide, essentially what you're doing in the all others as anchors approach is we are setting all of the item parameters to be equal across the two groups in one run. And then we're freeing up that constraint in a second run where we're looking at just item one. We'll free the item parameters to vary across item one across groups, but all the other items will be required to have the same item parameter in the two groups. And then we'll repeat that. We'll do another run where we compare, or we'll do another run where we take item two and we will free the item parameters in item two, but item one and then three and however many you got all have equal item parameters across the two groups. Okay, everyone, I want to hop in here and actually I truncated the last video, deleted part of it, and I wanted to re-record it here in a way that maybe makes a little more sense. So we were talking about constrained baseline. And before I do that, I wanted to show you something kind of the opposite of that called the free baseline model, because I think that'll make more sense just how I've got things kind of noted here. So what you're looking at on this slide is a situation where we've got two groups. We've got a red group and we've got a blue group, and we have A and B parameters for each of those two groups. So two parameter model, just keep it simple. And we got 4 items. And the numbers here you see, this comes like from old notation that used to be used in Literal. It's just where you number the item parameters that you're estimating. So these are basically just placeholders, right? This is just to show you that there's just going to be a number here. We don't know what it's going to be, but it'll be something, probably like 1, 1.5, something like that. B parameter could be anywhere between, -2, +2 in that range. But these are placeholders, and so when you see a different number, you know that it's a unique estimate. So this is the completely free baseline model. This is if you estimated both groups' item parameters separately, completely independently. This is what you would get. You would get an A parameter and a B parameter for item 1 for the red group. You get the same thing for item 2 for the red group, for item 3, item 4 for the red group. So 8 item parameters total, 2 per item, 4 items. And the blue group, you get totally different numbers over here, right? So you get a totally different A parameter than we got over here, a totally different B parameter than we got over here. And that's why this is a 9 and 10 instead of 1 and 2. This just shows you that these numbers will be different than these numbers and all the other numbers on here. So we're estimating 16 unique parameters in this free baseline model. So hopefully now the numbering system makes some sense. So I want to show you the constrained baseline model. And the constrained baseline model is probably the most commonly used approach in item response theory historically. And there's a good reason for that. It's part of the all others as anchors approach that I referenced in my paper and that we're going to use in this class. So let's take a look at what that looks like, the constrained baseline approach. Again, when you see a different number, that means something is uniquely estimated. And so in this case, you see something very different. In this case, you see that the number 1 appears here twice, and that is to denote that the A parameter for the red group and the blue group for item 1 will be the same number. So it's going to work out to be something, if you estimate things separately into two groups, and let's say the red group would have had like a 1 and this would have been like a 1.5 for the blue group, you'll probably get something around ballparkish 1.25 for both these, because we're making the constraint that they have to be the same, and that's part of the estimation procedure. The parameter is actually estimated under that constraint, so it's not allowed to do anything else. Same thing for the B parameter. You've got the same number for the red group and the blue group. And so this is what we mean by like items, right? So item 1 is the same, get the same parameters for the red group and the blue group for that item. You get different parameters for item 2 than, item 2 is different than item 1, but it's the same across the two groups. So hopefully that makes some sense what the constrained baseline approach is. And in this case, you'll notice we're only estimating 8 unique item parameters, not 16 like we saw with the free baseline approach. So this is sort of going to be our default model in the all others as anchors approach. And what we're going to do then is we're going to run these likelihood ratio tests one item at a time, comparing the model always back to the same baseline model. So this is the baseline model, the constrained baseline model that we used, that we're going to use for each and every item test. So let's take a look at the first one of these. I've just kind of copied over that baseline model up at the top here for reference. And we're going to run a model, what we might call the augmented model. In other words, it deviates from the baseline in some way. In this case, we're testing item 4. So everything down through item 3 right here is exactly the same. And to test item 4, what we have done is we now loosen that constraint on the item parameters for that particular item. So before, remember, we only estimated 8 parameters, and now what we're doing is we're estimating a unique parameter here for the red group for A parameter and the B parameter, and that's allowed to be different than the blue group's A parameter and the B parameter. So now we're estimating 2 additional parameters. And what we can do is we can compare the fit of these two models. So we'll get a -2 log likelihood for this model. We'll get a -2 log likelihood for this model. And which model will fit better? Ask yourself that, and I'll give you, you can pause the video if you want to see if you can answer that question. But if you have not paused it yet, I'll just plow ahead. So this model will have to fit better. The augmented model will fit better, right? Because these numbers are unlikely to be exactly the same. And so in this model up here, we're forcing them to be the same. So they're going to take on suboptimal values. So we have to get worse fit up here than we get down here. So what we're doing then is we're taking the difference in fit of these two models according to the -2 log likelihood, and we're evaluating that as a chi-square statistic. And degrees of freedom is going to be the difference in the number of estimated parameters. So this model estimates 10 parameters, and this model estimates 8 parameters. So you take the 10 minus the 8, and you get 2. So the difference in fit here is going to be it's going to be distributed as chi-square. You can look it up in the chi-square table or type it into Excel with the chi-square function, and degrees of freedom you use is 2, because that's the difference in the number of estimated parameters. So another way to think about that is you're estimating 2 parameters for each item, and that's going to be your degrees of freedom. It's the A parameter that's different and B parameter that's different over and above this model up here. So I should note, when you run these two models, the number you get for the 7 and 8 up here will be different than the number you get for the 7 and 8 down here, the A and B parameter down here. And that's because up here, these numbers are going to come out kind of somewhere in between what you would get if you estimated these two things separately. And so, like, imagine again, this is a 1, this is a 1.5. Down here, you're going to get a 1 and a 1.5, and up here, you're going to get something like a 1.25 when you're constraining that to be the same for that 7. Let's take a look at another example. This is to test item 3. And in item 3, you can see here we have we've gone back to the baseline model. And in this case, all we have done is freed the item parameters for item 3 instead of item 4. So these things, they kind of work completely independently. You don't build on models. In other words, you don't take the model over here and then further loosen it. You could do that, but it's usually not considered best practice. You sort of always go back to the baseline model. And instead of freeing the item parameters for item 4 to be different across the two groups, we're freeing the item parameters for item 3 in this case. And so same thing, take the fit of this model and the fit of this model, take the difference, evaluate it at the chi-square of 2, and that'll tell you whether or not you have significant diff for item 3. And earlier what we're looking at was whether or not you have significant diff for item 4. Okay, so you might be wondering then, well, why don't we just use the free baseline model and introduce constraints on that to test for diff? And that's certainly a logical idea, and then you can do variations of that. Remember, the free baseline model, you're estimating unique parameters for each group, for each item. And so you could do that. You could have a baseline model where you're estimating, again, unique item parameters for each group, for each item. And then you could compare it to an augmented model. So in this case, you're introducing a constraint instead of kind of taking a constraint baseline and freeing parameters. You're taking a free baseline and introducing constraints on it. So this particular model would look like this. Now you've got constraints on item 4. And you can see you're estimating 14 total parameters here instead of 16 like in the baseline model. The problem is the linking, right? If you remember what happens in this model, you're essentially estimating item parameters separately in each group. And usually the way the way the groups are sort of normed is that the groups have equal, or the latent means of each group is set to be equal. And that is not really what you want. So these groups really aren't linked in any way other than on theta. And so you're making an assumption that the groups have equal thetas, which is not really a valid assumption. So this is sort of frowned upon as the baseline. Again, same thing in CFA. In CFA, what you would do is you pick one item to be the anchor item. So, so actually, this would be like the baseline model where you have constraints on this item's parameters, and so you treat this actually as the baseline, and then you could test the other 3 items by introducing constraints onto them. Okay, let's take a look at the pre-baseline approach with Anchor now. So remember, when you're just talking about baseline model is completely free, the problem is the two groups are just not linked. You can't really say anything about their means because the means are estimated to be 0 in each group. And you also can't say anything about invariance because the nature of the item parameters is estimated with respect to those means that we were assuming to be equal, which we can't really do. So the anchor item model is the most commonly used one, both in CFA and also in IRT. So in CFA, it would look something a lot like this. Usually in CFA, you just pick a single item, and you set that item to be invariant across the two groups. In other words, you set the item parameters to be equal for the two groups for one specific item. So there's something important to say here about this, and that is there's an inherent assumption then that you have one item and that you know that item to be invariant. And the problem, of course, is that we don't usually know whether or not that item is invariant. With CFA, it doesn't tend to matter as much because we typically test all the item parameters kind of simultaneously, and we don't really worry about item level results with the CFA approach typically. So it works out really okay in that approach because what happens is if you were to have, let's say, diff on this item, then that diff would get transferred over to sort of the other item parameters, and that would come out when you test CFA. You essentially test all the items at once. And that's not what we do in IRT. And IRT is much more of an item level focused analysis. And so we're going to test each item individually. So the problem with this particular approach is that we have but a single anchor item, and we don't know whether or not this item is truly invariant across groups, but we're assuming that it is. But in any case, this will kind of set up what we're going to talk about a little bit next time. And you'll be able to, we'll talk more about kind of how you choose anchor items. But if you understand what you're looking at here, that's a good understanding of kind of how the anchor item approach works. So with the anchor item approach, this is the baseline model. The baseline model has one or more items where the item parameters are set to be equal for the two groups, and that links the groups together. If you think back to that linking topic we did, this serves as sort of the item that does the linking. And by linking these two groups on this one item, we can then compare the item parameter estimates for all the other items and test them for invariance. So this is the new baseline. The baseline already has a constraint in it. You're not constraining all the item parameters to be the same, but you are constraining one or more item parameters to be the same. And then the way you actually do a test is you test the baseline model again to an augmented model that is more constrained. So if you look at this model down at the bottom, it's identical to the one at the top, but we have introduced a constraint on item 4. So instead of estimating 14 total unique parameters, we're estimating 12 total unique parameters. And comparing the fit of these two models, we'll test item 4 for invariance. And it will be chi-square test again with 2 degrees of freedom because that's the number of difference in the item parameters estimated. And so this is the anchor item approach. And then we would to test item 2, for example, we would do the same thing, and instead of the constraint on item 4, the constraint would just be on item 2's parameters. So that's the anchor item approach. And the anchor item approach is often preferred over the all others as anchors approach. So you can see if you go back to this constraint baseline approach, what we were doing essentially is treating all the items as anchor items. And all the items, except for the one being tested, serve as anchor items. The problem with this approach is that if you have a lack of invariance on some of these items that serve as anchor items, that's sort of violating the assumption. The assumption is that these anchor items are invariant free. And so what happens if you have diff on some of these other items and you make them anchor items, it can actually give you type 1 and type 2 errors on the item that you are testing. So the approach that I prefer, and the one based on my work with Natalie Wright, who was a grad student here years ago, we looked at this and we found that kind of an iterative approach works better. And we'll talk about that some in the next video. Okay, so now you've got a pretty good feel of some of the issues involved in linking and kind of setting up and running these likelihood ratio tests. So there's a couple other outstanding issues we need to talk about. So we talked about the all others as anchors approach, and that's where you use that constrained baseline model, and then you free up item parameters for one item, and then you compare those two models, and that tests that one item for diff. Again, the problem with that is in the linking. So all the items except the one being tested are used for linking. And so if there's diff in any of those items, that diff can give you essentially errors on your item level test. So what you really want ideally is a number of very clean items to use as anchors. The other approach, if it was using just a single anchor item, there's really two issues with using a single anchor item. One is you're really putting a lot of burden on a single item on your test. So, in other words, with kind of two respects. One is that item absolutely must be invariant, and we don't ever know that. And second is you get poorer linking. So you typically get better linking with more items you have for linking, so long as those items are not don't have diff. So what we want to do is we want to find some smallish amount of items for linking to use as anchors that do not have diff and also are not just a single item, so that we can get a better kind of linking between the two groups. And that's what we're going to talk about in this short clip here. And those are some of the issues to face. So there's a couple of kind of things to tell you about people have tried previously, and if you read the Mead and Wright paper, you'll see all these talked about in there. And one issue is whether you do two-stage linking or iterative linking. So with two-stage linking, you test all the items for diff using the all others as anchors approach. So constraint baseline, free each item parameter, free the item parameters for just one item, compare the two, do that for all the items. And in two-stage linking, you pick all the items that don't have diff and you use those as your anchors, and you're done. In the iterative linking, you make those items your anchors, and then you retest all the remaining items for diff again. And then you would kind of continue this process. And the idea is you might find new items that now have diff with this new kind of linking approach here. And again, you sort of continue that process until it sort of converges, and convergence can take kind of a longer time in some instances. Um, the approach that I recommend in the paper, the Mead and Wright paper, is called the A5 approach. And the A5 approach is essentially a way to choose items for anchor items, right? So the anchor items, the other thing I should mention before, if you go back to that slide about anchor items, when you have an anchor item, in this case it's a single item, you cannot test that item for diff, right? You just can't do it. It's always constrained, even in the baseline, to be the same. So the only items you're testing for diff are the items that are not your anchor items. So when you make an item an anchor item, it's important that you know that item really doesn't have any diff in it. And that's why we test for diff first before we choose an item for anchor items. Um, in the A5 approach, or the max A5 approach, that was just based on a simulation study with, I think it was 25 items. And we said what we recommended that you do is choose items for anchors that don't have diff. So it's important not to have diff, right? That's sort of an assumption of anchor items, no matter what you're doing. So you're going to run this all others as anchors baseline model, and you're going to test each and every item for diff using that approach, because that's a good starting point, right? You don't know which items have diff, which don't. You use this all others as anchors approach, and you test for diff. And then what we're going to do is we're going to take up to 5 non-diff items that have the highest A parameters. And there's a couple of things to say about this. First off, A parameters, you'll remember, is really closely related to item information. And the idea is by choosing items with a really high A parameter, you get a lot of information from those items. So essentially, the items with the highest A parameters are the best items, right? They're the best items you've got. And if they don't have diff, those are going to be some optimal items to use as your anchors. Now, why don't we just choose all the items that don't have diff from the first run? Well, as it turns out, um, since you can only test items in the anchor item approach, only test items for diff that are not your anchors, if you were to have a problem in this first run where you're using all the items as all the other items as anchors, if you were to have a problem, you accidentally find no diff for a diff item, then that item becomes one of your anchor items. You can't test it again, right? You're not testing it, you're assuming it doesn't have diff. And so that can actually mess up your test. And so the idea is you don't want to choose any more items as anchors than you have to, because you want to be able to test the items for diff again if possible. So we're going to choose up to 5 non-diff items with the highest A parameters. Now, this number 5 was based on our simulation, but it worked out to be about 20-ish percent, 25% of the items. So if you only have 8 items in your scale, you probably don't want to use 8 for anchor items. You probably want to use something more like, I don't know, 2, 3, maybe 4 at the upper limit. But, and then when you're running your model, those anchor items don't get tested again, right? They're assumed to be diff free. So don't take all the items that come out as not having diff after the initial run, because some of those we know are going to be errors, right? They're going to be essentially like false negatives. And so we only want to choose the smallest number we have to get good linking. And then we're going to use those anchor items and use the kind of the step-up approach, using those items as anchors for the final test of diff. So typically what I would recommend in the manuscript, you might mention this, but you wouldn't interpret these results from this first run, because those are just used to identify the anchor items. So the whole point of what you're doing in number 1 is not to do any diff tests. It's just to do some initial diff tests in order to find the anchor items. And once you have the anchor items, you ignore the results of this first guy up here. And that's important. That's something that people commonly get wrong. I see when I do grade projects, they'll spend a lot of time talking about the results this first test, and you don't do that. The point of this first test is just to figure out which items might make okay anchor items. Once you have your anchor items, you get to step 3. You really don't, you kind of report these up here briefly in passing, but you don't revisit those results in the discussion or anything like that. You only take the results in this third step using this anchor item approach.